Hi everyone. So I'm going to explain you one of the projects which is needed by Duke University for getting my certification on on the regression. So to start with, basically, the problem is that we need to predict or create a model for the predicting energy output from temperature, ambient pressure, relative humidity, and exhaust vacuum. So this is the raw data what we get from like the Duke University questions. So this data is provided by them. We are going to use this data to build the model. Now, first part of this one, what is the modeling approach? So this is basically a supervised regression problem because we know what are the independent variables are and why we know what is the dependent variables and we want to predict something which is a continuous value, like it's not a classification, it's not a yes and no or some classification of dog cat or something. It's a continuous value. We need to predict one number which is a continuous value. Okay, so now let's move to the second part, the model building part. Right, so we have decided, fine, this is a continuous and this is a supervised regression model we're going to use. Now on this model creation part, the first thing is we have four variables, right? And we have about, if not mistaken, about close to 10,000 data. The first thing what we want to do is create a strategy, right? What should be our approach? So my approach was first, I'm going to divide the data into three parts. First part is the training data. So which would be 70% I'll put as a training data out of the 10,000, right? Then another 15% I'll put as a validation data. So after we train our model into maybe, different things, I will try to validate it if the model is accurate or not. And the last part would be the test data. Means once we decide, okay, this is the model we're going to use, then we'll test it with the test data. So what I did is basically in the column G here, I created random numbers and then I basically sort them in whatever ascending or descending order. After that, you basically put a tag of what is the data. So 70% I divided in training data, then another 15% validation data, then another 15% test data. Okay. So after that, I basically put training data in one sheet, validation data in this sheet, and the test data in this sheet. Now let's come to the training data, right? So the now for the training data, I'm going to, so we have our independent variables, right? So these are the independent variables, and this is the dependent. So these are our x's, and this is our y. Okay. So to do regression, basically, you can go to the Excel here, the data tab right here, you can find it. This is the home, this is the data tab. Data tab, normally there would be like, a data analysis. It is available in the add-in. It doesn't come now naturally. So you need to go to add-in and then select add-ins and you have to add data analysis. So when you click on the data analysis, you probably see things like this, ANOVA and everything. So you drop down, it is alphabetical order. So you select regression. When you click on regression, it's very simple. Like you need to select your Y range, you need to select your X range, then you click OK. You can select all these things. For now, it is not needed. So I'll not do it. So once I do it, so I selected all the four variables here as my X's. This one is as my Y. So this is the result then we'll get. Right. So basically what we can, okay, I'll focus on the major parts. So basically this is the adjusted R square, right? So the adjusted R square of 0.93 means basically 93% of the variation in the output value or our energy output can be explained by these. Another, let's say 7% is some external factor which is not captured in these four variables. Okay. So this is statistically significant. You see, all the p values are quite high. When we get to the equation, so this is the intercept, means like, if everything else is zero, where will the line intercept? Correct. Then we have the temperature. So temperature, the coefficient is 1.98. Okay, how do you read it is your every 1 unit change in temperature is going to change my power output by minus, so there is a minus symbol here, by minus 1.98. Okay, then we go here with this lower 95 and upper 95, which means 95% of the time when a temperature is increased by 1 unit, the whole power output is going to drop by 2 units, which is by 2.01 units to 1.94 units, which will happen 95% of the times. Okay, so since this one, so now what we did the analysis with four variables, right? So we don't know whether we actually need four variables or maybe, three variables should be enough to do the interpretation. Correct. So what we do, we look at the p-value. So I keep increasing the p-value from here. When you go to this one, you select number, you keep increasing the p-value, you can decrease the p-value. So I keep increasing the p-value. You see, because the model is statistically significant, a lot of these p-values are like, you can say a lot of zeros. So only this ambient pressure started showing some number, which is, 3 number in the p-value towards the last. Apart from that, if you look at the t statistics, so it has the lowest t, which is 5.92. So we can easily interpret, okay, if we want to try another model by dropping one variable, so probably ambient pressure is the one we should drop. That's what we did. Same way, you go to the training data, you do the analysis. Now, instead of selecting all the four, you just select these three and you do the regression analysis. Now, here, one thing to notice that sorry, yeah, the adjusted R square is almost the same, which means the incremental value what ambient pressure was adding was not significant. Means whatever explanation we are able to get from these three variables, the fourth variable, ambient pressure was not adding much incremental value. So we can kind of, we already can conclude that, okay, fine, so these three variables we can take and we can drop ambient pressure because there is an incremental calculation cost involved, there is incremental data collection cost involved. So if it is not adding significantly higher value, we can drop ambient pressure as one of the variables and we can build our model on these three variables. But I just wanted to make sure that, okay, that is correct. So in the validation of the data, what I did, so this is basically the calculation. What I did, I calculated with four variables and I calculated with three variables also. So these are the numbers basically you calculate and this is for my own calculation, which is the error. Error is basically the delta between your actual versus the predicted value in the test data. And here absolute error, because if it is positive or negative, then it will neutralize each other, right? So I took the absolute value to see actually how much is the total error. And sometimes, you can use the squared value also. So basically, this is the square of this value. Same way for the three variables, this is the equation, right? So now we go to the model comparison. Now let's focus on the top three rows first. Okay, so in terms of model comparison, you see this validation R square is almost same. It's 0.938 versus 0.9307. So it's just the very marginal difference, which means it's your call, because if that margin of difference is it's literally insignificant. So for me to when I'm predicting the power output, I'll rather take this than all four because of the additional cost and effort involved. Then what I did, I then do it in my test data. So this is remember when we started from the raw data, we put 15% of our data as test data, correct? So then I basically did the calculation in the test data, exactly the same thing. Okay. And then this is what. So now you see all your R square is also within the range, which means when we're saying, okay, 93% can be explained, like within the real life scenario, when we did not take this one in the test data, it is still able to explain 92%, which is also significant. So we can conclude that, okay, this model is good enough for us for the implementation.